Quantum mechanics, the mysterious science that governs the tiniest particles in the universe, has once again made history. The 2025 Nobel Prize in Physics has been awarded to John Clark, Michel H. Devoret, and John Martinis, three scientists who showed that even large systems made up of billions of particles can exhibit quantum behavior under the right conditions. Understanding quantum strangeness. At the smallest scales, inside atoms, the laws of nature behave very differently from what we see around us. Tiny particles can exist in two or more places at the same time, a phenomenon known as superposition, and they can also pass through solid barriers, an effect called quantum tunneling. These behaviors sound impossible, but they're proven facts of the quantum world. However, large everyday objects made of those same particles don't behave that way. That's where the 2025 Nobel laureates made history. They showed that even macroscopic systems can display quantum effects. The Nobel Committee recognized their work for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. In simpler terms, they managed to make a large electrical circuit behave like a single quantum particle. Their experiments in the 1980s demonstrated that entire systems, not just electrons, could jump between energy levels and tunnel through barriers in a way that defied classical physics. The story begins at the University of California, Berkeley, in 1984 and 1985. At that time, John Clark was a professor exploring superconducting phenomena, Michel Devoret was a postdoctoral researcher, and John Martinis was a PhD student. Working together, they used a setup similar to one that had already won a Nobel Prize in 1973, the Josephson junction, developed by Brian Josephson. A Josephson junction consists of two superconductors separated by a thin insulating layer. Under normal circumstances, the insulator blocks any electrical flow. But when the materials are superconducting, something extraordinary happens. Electric current can tunnel through the insulator without resistance. Superconductivity itself is a quantum phenomenon. The electrons move together like one massive quantum wave. Building on Josephson's discovery, Clark, Devoret, and Martinis isolated their setup extremely carefully from environmental interference. Even a tiny disturbance, a vibration, a magnetic fluctuation, or thermal noise could destroy the fragile quantum effects. Under these ultra-controlled conditions, they observed something never seen before. The entire circuit behaved as a single quantum object. It could only exist in certain discrete energy states, not anywhere in between, just like an atom. And it could jump or tunnel from one energy state to another. This was the first experimental proof that quantum mechanics could govern a system made of billions of particles. At the time, this discovery didn't create big headlines, but decades later, its significance became clear. It was the foundation for one of the most revolutionary technologies in development today, quantum computing. By showing that macroscopic circuits can behave quantum mechanically, they paved the way for quantum bits or qubits, which are the fundamental units of quantum computers. Interestingly, John Martinis would later lead Google's quantum AI program, building superconducting quantum processors that directly stem from this early research. Their discovery also answered a question that puzzled physicists for decades. How large can a system be and still behave quantum mechanically? While that question isn't completely resolved, their work proved that quantum behavior isn't limited to atoms. It can extend to engineered systems visible to the naked eye. As physicist Rajamani Vijayaraghavan from TFAR explained, from a fundamental perspective, it showed that macroscopic systems can show quantum behavior. From a technological perspective, it set the stage for building quantum computers. In essence, the 2025 Physics Nobel laureates didn't just study quantum physics, they brought it to life on a scale we could measure, control, and use. Their experiments turned abstract quantum theory into practical technology, ushering in what many call the dawn of the quantum age. Thanks for watching. If you enjoyed this explanation, please like, share, and subscribe for more deep dives into Nobel Prize discoveries, science, and innovation.